Hi, my name is Robert Dickerson, and I'll be discussing genetic algorithms for my senior project. I am using them to optimize a solution for the traveling salesman problem, and I will share a little bit with how they work with you and how you might be able to use them to solve other problems that might help you in the future and might spark your interest in seeing how they work and wanting to learn more as they did for me. Because I think they're awesome, and I hope this presentation will help you to know that they're awesome too and help you to kind of have some enthusiasm towards them and find a way that you can use them. And so I'm just going to share, I prepared a little PowerPoint to share some of this stuff. And so I just want to kind of start off with a very simple thing is a genetic algorithm. It uses children, and these children can be randomly generated. They'll be nodes in a sense in your algorithm, and these nodes will either be randomly generated or they can come from data sets that you receive, or if you're using them to try and identify something, they will come from the data that you have to start with. And it doesn't have to be right. That's the biggest thing about the algorithm, is the point of it is to help you get the right solution or the best optimized solution. So starting generation can be terrible and unpredictable. And this generation will grow, and I'm going to tell you how it grows in just a moment. But each child will have an opportunity to experience something called crossover, mutation. Those are the two that are crossover and mutation are the two that are used most with genetic algorithms. And each generation will be changing, and your solution will end either when it reaches the set amount of generations that you have entered, or when you have reached an optimized result according to your criteria that you started with. And so depending on where that lands, this is what you should end up with. Kind of the best result possible, better than average. And so each child will be presented with a fitness variable. And this is common among most, if not all, genetic algorithms, is basically the success or survivability of that child node. If it has a high fitness, usually the fitness level will range from 1 all the way down to 0.1. And with that scale, usually you can safely assume that any child below 0.5 is not going to be very likely to survive. And depending on how you write the algorithm, it will cut off at 0.7 or 0.8, depending on how strict you want the algorithm to be. And it will kind of just eliminate those children, unfortunately. But they weren't helping to solve the problem. And so that way it can produce more in future generations. And we'll talk a little bit more about it with crossover mutation right now. So crossover, it's you're combining the parents to form something smaller. For instance, pizza and pineapple might form pineapple pizza. And then mutation, obviously, with the Ninja Turtles is a safe thing. But these aren't exactly with genetic algorithms. This isn't exactly how it turns out all the time. And so with crossover, you'll take two parents, and we'll assume that their lines are strong, and we'll form a child out of them. And the crossover will create one child with, let's say, 30% of one parent and 70% of another. And a similar child will get the other half of that crossover. And as you can see, we'll be assuming that these integers are cities in the traveling salesman problem. You have 1, 2, 4, 3, 5, 6, 1 for the first parent, and 1, 2, 5, 3, 6, 4, 1 for the second. And as you can see, the crossover happens right here at the 5 and the 4, and it goes all the way back till you hit the 1. And it's a little bit different in traveling salesperson problems, because you have a select number of cities. Now, if you use this method on other types of algorithms or to solve or other types of problems to get a solution, then sometimes you'll get different types of crossovers. But this has to stay in that bounds, otherwise it'll be immediately cut off. And you can allow it to produce results that just don't work, that are invalid. And those results will probably get a fitness score of 0 or down at 1 because they can't be used and they need to be eliminated. And then double crossover is just taking a section or crossing two pieces, two smaller sections. So it's like 50-50, but the 50s are cut into 25-50-25. And this here is an example on the right side where it cuts off at the 4 and the 8, and it goes here, but it finishes right before the 9 in that center section. An example of mutation is when a parent completely will change to not necessarily look really like anything of the original. And this is okay. This allows parents that didn't do that well, that children nodes that didn't have a high fitness level, to become parents and mutate and possibly raise their fitness level via this mutation. It could also lower it, but this gives that diversity that a real generation of people will have. And it will allow that kind of Darwinistic experience of cutting stuff off that isn't helpful. And this is how your algorithm will be able to learn even better by handling these unknown cases. And this will be very useful in solving algorithms where you want it to be able to give you some information that you weren't planning on. This is a visual representation of the traveling salesperson problem after it's been solved. And you can see that some of these cities, especially in the middle here, it might look confusing depending on how you do your route. But this is the optimized solution for that specific set of children and cities. And so you can see that it is a very useful problem, and it has been done before, and it's how Amazon does their inventory. And so I thought it was really important to learn, and something that can greatly help me with future jobs, especially if I want to work at a company that does marketing, that can use this to help them progress. And that is my senior project. That is my Sped talk, and I've really enjoyed learning. And Brother Burton has helped me learn a great deal of this project. And I know that if you want, you can pretty much do any project, because we are capable at this point in our lives. And this is good. Thank you.